So we have been walking through our discussion of flowing electricity. I just wanted to do a quick review. These are my old notes that I used to do lectures off of, and this is where I started. We didn't take notes on this, but a comparison between gravity and electricity. Reason we did this is that in past years there was a big chapter in first semester about gravity, so I wanted to show how electricity is similar to what we learned about gravity. We could use all of our same tricks. Okay, so then the first thing we did is we introduced this concept of electric potential, which is called voltage. There's actually three words that go on here: electric potential, voltage, and another thing called electromotive force, or EMF. And I'll tell you the historical reason for that, but basically all of those words can be summed up in the word voltage. And since that's the word that we're most familiar with, voltage, that's the word I want to use. And it's an electrical potential energy. I called it an electrical pressure, and so did Bill Nye. Uh, we talked about that, and then we said that voltage is sometimes called potential difference, because only a difference in voltage causes charge to flow, much like a difference in temperature causes heat to flow. If you had two things that were both at high voltage and you connected them together, there might not be any current between them if they were the same. I kind of intimated this when I was talking about charging your cell phone, and you have to use a 5-volt USB cable to charge your cell phone, because your cell phone's battery is somewhere between 4.2 and 4.8 volts. You need more voltage to push the charge into the battery than the battery is trying to use to push charges out. Same thing is true in your car. If you have a gauge for your charging system and you drive down the road, you might notice it says 14 volts. And yet a car battery is 12 volts. That's because when the engine is running, the alternator or generator in the engine puts out 14 volts in order to shove charge back into the battery of the car. I once had a car whose charging system failed, and I noticed that the meter started saying 12. That meant that I was running the car off the battery. And you can do that without the headlights on. You can drive for a while. I'm talking an hour or so off the battery, but I wouldn't go too much further than that. And then your battery is going to be dead. So we said that Alessandro Volta is the father of the electric battery. We also said that capacitors are another way to store voltage and charge. Then on the other side of this line, the movement of charge is called current. Now there's something that I did not say that I'd like to say now. I seem to have given current a little bit of a short shrift. The idea is that current is the flow of electrons moving down wires. But ideally, people didn't know that initially. I shouldn't say ideally, I should say initially. People didn't know that. So we always pretend that positive charge moves. And this idea that positive charge is doing the moving is called conventional current. In reality, electrons are moving the opposite direction. So when you look at a battery, like a little AA battery you might have, there's an end that has a little dimple on it, and then in a Duracell battery, that's the one that's colored copper, and that's the positive terminal of the battery. And we always imagine that the electricity is coming out of that positive terminal, and then going through the circuit like the remote control or whatever you got, and then going back into the battery through the negative terminal. But the truth of the matter is that electrons are shooting out the negative terminal, going through the circuit backwards, and coming back in the positive terminal. Does it matter? No. In all but the most really critical applications, it doesn't matter which sign of charge is moving to create the current. But we just pretend from now on that it's conventional current. Another thing that was mentioned in your book, and you've done your outline, so you know this, that the actual electrons in a wire are moving very slowly, only about a meter per second, only about walking speed for high school students in a crosswalk. That's so funny. Sorry. But the current, the overall current moves quickly, and the reason for this is that the wires are chock full of electrons. So the minute some of them start moving at one end, they push into all the other ones, and the electrons start moving everywhere in the wire virtually at the same time. Not quite. There is a limit to the speed at which these kinds of phenomenon can move through a wire, but it's measured in hundreds of thousands of meters per second, not single-digit meters per second. But the individual electrons are not moving that fast. You can imagine a crowded hall of people, and then if somebody shoves somebody, they bump into the person in front of them, and that interference, that disturbance, it moves through the people probably faster than the people are actually moving. And of course, this is the thing I forgot to say in class: current is abbreviated with the letter I and measured in amps. So voltage causes current, but current is limited by resistance. This is what I ended with yesterday or Monday. That voltage causes current, but current is limited by resistance. The resistance is coming from either the wire that it's traveling down or maybe something that it's being asked to do. Like maybe it's being asked to go through a speaker and do something to make noise, or go through a light bulb and do something to make light. And all those things cause resistance. Even the wires themselves, the shape and the length of the conductor determine the resistance. So skinny wires have more resistance than fat wires. So when you see lots of electricity going someplace, it's usually going on pretty fat wires. This came up with me one time. I was using an extension cord with a table saw because I wanted to do some sawing in my driveway, big long pieces of wood. And I just grabbed a regular extension cord and I started sawing, and the motor didn't seem to have a whole lot of oomph. And it would slow down as I put the wood in, and then I felt the extension cord and it was hot, and I realized, oh my, I needed to get an extension cord that had fatter wires inside. Resistance gets the letter R, and it's measured in ohms. Ohms get this symbol, the omega. Ohm's law is the most important thing here. We're going to be using this for the next couple of weeks as we investigate circuits, and it's written as V equals I times R, so there's a relationship between voltage and current. I'm going to do a little focus here. This does not look like it's in perfect focus. We try 16%, 12%, no, 19%, 20%, 24, 27. Damn, 27 is the number. Okay, here is a way to write Ohm's law in a triangular fashion. I might have shown you this earlier in the year. And that allows you to do all the algebra on this. So if you're looking for V, you cover up the V with your thumb, and that's equal I times R. If you're looking for R, you cover up the R with your finger, and that's equal to V over I. And if you're looking for I, it's equal to V over R. I give you this triangle as my gift. Take the two that are next to each other, put them in the bottom of the pyramid, take the other one, put it in the top, and you now have a machine that does the algebra for you. Okay, so this is where we're headed today: electrical energy and power. And I can pretty much just kind of do it right here on this little screen. Power in electrical circuits is equal to the voltage times the current. So if you look at this Ohm's law, you'll see that V is a number that tells you the electric pressure. If there's more voltage, there's more electricity going on. I tells you the flow. If there's more flow, there's more electricity goes on. So these two are positive, or as I said last chapter, they're directly proportional to the thing you're studying. In R, unfortunately, is a reverse concept. It's an inverse. The more resistance there is, the less current there's going to be, the less electricity is going to happen. So if you want to form the equation for power, which of course, according to Bill Nye, is measured in watts, then you need to multiply your two positive things together, your two direct proportionalities, your two things that are that show you how much electricity you have, the voltage and the current. And the way it works out is voltage is joules per coulomb. Current is coulomb per second, so you wind up with joules per second, which is the unit of a watt. That's where most of us hear watts to begin with, is from electrical things. So power is voltage times current. And because you have Ohm's law, you could always get rid of one. Like if I didn't know the current, I could solve for the current with Ohm's law, which would be, V over R. And then what I would do is I'd put that in, and then that would be two V's on the top, V squared over R. So that's another formula for power. It's just as good as this one. It's just if you don't happen to know the current and you do know the resistance, you can use this. This one's really convenient around the house. Because the voltage at your house is fixed at 120, so you got 120 squared on top, and then there's a relationship, an inverse relationship between power and resistance. Another one that you can form by getting rid of voltage, if you don't know the voltage, is I squared R. I squared R, that's where you get rid of voltage by putting I times R, so you have I times R times I again, I squared R. But this one is special. It has a name. It's called Joule heating. And the reason is, Joule heating is kind of a negative concept. It's where power or energy or current, specifically going down wires, causes them to heat up. The reason the birds sit on the power lines is that they're warm. Thank you. And I told the story about my extension cord. Joule heating is what's responsible for that. And you can see that Joule heating depends on the current. The more current that flows, the more power is going to be dissipated by the wires. And power dissipated by the wires is not power that you are allowed to have at the other end of the extension cord. That's why my saw motor slowed down. So this is measured in watts. I said that before. But when you buy electricity from Southern California Edison, they charge you in kilowatt hours. Now, this seems a little weird. It's got watts inside of it, but it's times hours. So, what is this really? Well, 1 kilowatt hour, and that's multiplication, that's why I put the little dot in there, is 1,000 watts, that's what a kilowatt is, times 3,600 seconds, that's what an hour is. So it's about 3.6 million joules, and joules is a unit of energy. So even though this unit that you're paying for from Southern California Edison is a kilowatt hour, it's got watts in it. You'd think it's a power. It's not a power. It's an energy because it's been multiplied by time. So you're really only paying for your energy. Now that's at residential. That's at residential places that you pay for your energy use. They don't care how fast you're using it. If you are a commercial customer, they might be charging you for your power, the rate at which you're using it, because that costs them extra money and equipment to be able to develop that kind of power and send it to you. So if you have a lot of printing presses and things, big heavy machines that operate, then you might be on a different deal. But we residential customers, we pay for kilowatt hours. Just in case you care, you can take a look at your family's electric bills and you will see that you are paying about 15 cents a kilowatt hour, although it is a tiered system, T-I-E-R, tiered system, meaning that if you start to use a lot of energy, they start charging you more per kilowatt hour, so it's a sliding scale. They also charge you for delivery of the electricity separately. So look at both places on the bill. You're paying for the electricity itself, and you're paying a fee to maintain all the equipment that delivers it to your house. After all, what good would the electricity be without the wires that bring it to your house? So all told, there was a time when I was paying about 36 cents a kilowatt hour, and I was getting electrical bills that were $400 to $600 a month. Now, you may not think that's a lot. I have some friends that live out in Silverado Canyon, and they pay less than $80 a month for electricity. So I went through a period of time where I replaced all my light bulbs with fluorescent lights. I looked at everything. It was got rid of the extra fridge in the garage, that kind of stuff. And I kind of realized that what was going on was the tiered system was getting me. So I put solar panels on the house, and now I use very little of Edison's kilowatt hours of electricity. And my solar does the rest. It's kind of nice. If you want to figure out what it's going to cost you to run a certain electrical appliance, here's a fun handy dandy formula. Take the power of the appliance, but express it in kilowatts. Now, you can find this on the back of any appliance. There's a sticker next to where the cord goes in, and Underwriters Laboratories or one of these other groups mandates that you put a sticker on there, and it says what its maximum power consumption is. Doesn't mean it's always consuming that much, but that's a good idea. Then the time in hours that the appliance is on. So you've created kilowatt hours, and then multiply by the rate that you're paying, which your book tends to say, oh, it's 9 cents kilowatt hour. In California, you can say it's 15 cents. But if you are a big user of electricity, if you just built one of these Rossmore McMansions and you have lights under every crevice of your house and you leave them on all the time, and then you're probably paying a higher rate for electricity. But you can figure out what it's going to cost. And then here's another formula you might need. Now, these are ones you're going to use in your life, okay? I'm teaching them to you because we're learning about electricity in this chapter. But these are things you're going to use in your life. You are going to care about this when you have your own house. And you are going to care about this one. Oh, by the way, when you don't have your own house, when you live in an apartment, utilities are often included in the cost of the rent. So that means your electricity is free, right? Your hot water is free, your gas is free. You can just use as much of that stuff as you want. Somebody else is going to pay for it, right? Okay, apparently you haven't thought this through. Your rent is predicated on an average use of electricity. If the apartment complex discovers that you are a super user of electricity, they may start to increase your rent because they need to turn a profit on their property. So you shouldn't be wasteful just because your rent includes utilities, okay? This will help you out a lot. Buy appliances that use the least amount of power. Turn them on the least amount of time. Make sure you don't go into a higher tier so your rate is low. And then the product of all three of these numbers will be as small as possible because all three of these numbers are as small as possible. My grandfather, oh, bless his heart, he was a career Navy man, and I used to get sent over to my grandparents' house for what they called vacation. And I didn't think of it as a vacation, but I now understand it was a vacation for my parents. And I'd stay with them for a week. And if I was playing in a room and doing something and I walked into another room, I'd hear my grandfather go by and turn off the light in the room that I was in that I had forgotten to turn off, and he would say the same phrase every time: "When not in use, turn off the juice." I think it must have been a thing from his days in the Navy. When not in use, turn off the juice is just his mantra. All right, let's get to the last thing. We can get done with this. Many of you will have an electric car, and the electric car's battery capacity is measured in these kilowatt hours. Okay, here's a secret. Teslas have sometimes numbers in the model designation. So when you get a Model S, you might have a 100D. Well, 100 is the number of kilowatt hours in the battery. That can help you figure things out. So sometimes cars have as little as 30 kilowatt hours in the battery, but a lot of times they have more. By the way, the fact that this is kilowatt hours and this is kilowatt hours has got a lot of people thinking that we should have electric car chargers in our house that, in the event of a power failure, can run our house electricity from the charged battery of your electric car. See, that'll keep the refrigerator running. That'll keep the heat going if it's the dead of winter in Montana or someplace. Anyway, here's what you need to do. Take the capacity of your battery in kilowatt hours, somewhere between 30 and 100 kilowatt hours. Then divide by the voltage of the charger that you're using. If you just plug it into the wall, that's 120. If you have a special built-in charger, that's usually 240. And then the current limit of the charger. Now, this may be hard to find, but definitely you could say that it's the circuit breaker that the thing is plugged into. So if you plug into most household outlets, the current limit is 15 amps. So 120 times 15. If you divide the kilowatt hours of the battery by that, that will be the time to charge the electric car from nearly dead to full. My 240 volt charger has a current limit of 36 amps. That's the machine that limits that. It's on a 50 amp breaker, but 36 amps is what it'll hand to the car. So I can figure out how long it would take me to charge the car. And there's pluses or minuses. Batteries in electric cars charge faster when they're deader and slower when they're liver. And temperature has a lot to do with it as well. Okay, so electrical power is V times I. We'll use that in the future when we do some problems. And these are the things you need to know about electrical energy in the house and in electric cars. Thank you for your attention.